So we will continue where we picked up last time. And if you remember, we did this diffusion equation where we were looking at how the frequencies diffuse, how higher frequencies diffuse faster than lower frequencies in the diffusion process. And we did that with Dirichlet conditions on the sides. Today we will continue picking up on Newman conditions, and then we'll continue doing a few more examples with coupled equations, and then a nonlinear diffusion coefficient, and then we do 2 dimensions. Hopefully we cover 2 dimensions today, and then on Thursday we will start with Navier-Stokes, with fluid mechanics, and derive the Navier-Stokes equations from a different approach. I hope you saw my announcements yesterday about what's going to happen through November and December. And please read those carefully. If you have any questions, let me know. And if all goes according to plan, things will just go smoothly. Also, I had the announcement on the final exam, so pay careful attention to that. Specifically that from what I've seen on your homework assignments, you will be asked about your homework assignments essentially. So whatever you have in your homework assignment, you should make sure that you understand what you have in there, because there are some common themes that I saw throughout all of the assignments, the projects. So I'll pick some questions about coding mostly. They're reasonable questions, obviously, but anything we covered in class, you should be able to explain. I'm not asking you to know Python by heart, but at least know how to use the things we discussed in class. Okay, so the purpose is not to punish you or anything like that, just to make sure that you are understanding what I'm trying to teach you, right? So that you don't get in trouble next semester. Okay, so let's continue with Newman conditions. Last time we did Dirichlet conditions on the diffusion equation. Let me just go to the Newman boundary conditions. If you remember what we did at the beginning of the semester when we were doing linear systems of equations, the problem we were dealing with was a steady state diffusion problem. So it did not have the time derivatives, agreed? And we converted that into a system of linear equations, right? So if you recall, let me see, where's the annotation thing? Yeah, so if you recall, we had only this term, there was no time derivative, so it was a steady state problem. And then we had to do something special at the boundaries when we had Newman conditions. For Dirichlet conditions, the equation is specified, the value of phi is specified, so we didn't need any equation. But for Newman conditions, we had to use this ghost point, etc. So the same thing applies when we are trying to solve the unsteady diffusion equation or advection numerically with the Newman boundary condition. We have to figure out what the equivalent ODE at those grid points is. So if we do that, we have this kind of specification at the boundary. It's always, the Newman condition is always normal to the boundary. So if your boundary is y, perpendicular to the y-axis, then your Newman condition is d phi by dy. If your boundary condition is perpendicular to the z-axis, it will be d phi by dz. Why? Because that's the flux that's gonna go inside that face, right? It doesn't make sense to have a d phi by dy on an x boundary, on a boundary that's perpendicular to the x-axis, because that's only changing along the boundary. It's not affecting inside the volume per se. Even if this is 1D here, it's not affecting what's inside. So the Newman boundary condition is always normal to the boundaries. So it's given to us, specified by this condition, and then if we take our diffusion term and try to discretize it at that boundary at point n, then we end up with this phi n plus 1. If we're still following through the central discretization approach for the diffusion term, we end up with this phi n plus 1 that doesn't exist in the list of variables, in the list of unknowns that we are trying to solve for. It essentially extends outside of the domain. But then we're going to keep that for a minute, just temporarily, and we're going to eliminate it using the information from the Newman condition, like we did with the linear system of equations. And to do that, we discretize the boundary condition itself at the boundary, and we will also use a central scheme to be consistent with the order. Everything is done as a central discretization, so why not we continue a central discretization on the Newman condition. So if we do a central one on the Newman condition, what you get is d phi by dx is at point n, is phi n plus 1 minus phi n minus 1 over 2 delta x equal beta. So you know beta, you know phi n minus 1 is part of the solution, and we are left with phi n plus 1 that we need to relate to beta and phi n minus 1. So you can go ahead and do that. And then you invert. So essentially you're inverting this equation to extract phi n plus 1 from it and express it in terms of all of the quantities that we are solving for. So now phi n plus 1 is function of beta, delta x, and phi n minus 1, which is good. So then we take this phi n plus 1 and plug it back into this equation at the boundary. So this is only the equation at that boundary point n. And you substitute, and you finally get this ODE at point n where there is a Newman condition. So everywhere else we have d phi by dt, this standard discretization here. Everywhere else you have it. At this boundary you might have a Dirichlet condition, then d phi by dt is 0. If you have a Newman condition, you have to repeat the same process, and you'll have a d phi by dt at point 1 in terms of the Newman condition here, and this ODE applies at this point. So when we are building the right-hand side for solve IVP, this is going to be our generic formula everywhere, and we can use the standard numpy.roll, etc. And then we're going to go and adjust the boundary points at this point and at that point, like we've done, we've normally done. Okay, and then we can continue. Let me clear this. We can continue with this similar approach on the other boundary. So on the left boundary, if you had d phi by dx equal alpha, so I use alpha on the left boundary and beta on the right boundary, you do the same thing, but right now d phi by dx central is phi 2 minus phi 0 over 2 delta x. Phi 0 is the ghost point in this case, and your discretization results in this ODE at the left boundary. Of all boundary conditions, the hardest one is going to be the Newman boundary condition. That makes sense. Because it requires a little bit of work. For Dirichlet, it was easy. The right-hand side was simply 0, or with your homework assignment, it was a function of time. So you can derive that, but it's kind of easy. You just set it straight in the right-hand side. Here you have to do a discretization and figure out how to code it. So we're going to code this up together. So we will go back to our diffusion test case that we did, where we advected the Gaussian or the step function or the frequencies. So that notebook, grab it, and now we're going to implement, to experiment with Newman conditions on the left, on the right, or on both. Okay, so let's go ahead, grab your Jupyter notebooks. I'm gonna open the one you guys worked on last time, that we worked on in class together. Find it first. So I think it was called like in-class diffusion problem, whatever, 2025, right? So we had this. Okay, if you remember, this is what we were doing. And let's just solve it again, solve it one more time to make sure that everything is working. So I'm going to change the initial condition here and go back to perhaps the Heaviside function. So let's see, this is the Heaviside, and then let me solve this. Okay. It took a minute, but then it ended up solving it. So the final solution was everything was diffusing. Now this is Dirichlet condition, Dirichlet condition 0 on both boundaries. Okay, so this is Dirichlet 0 on both boundaries. Next, we will do a Newman condition. So we will start with the Newman condition on the right-hand side. Let's say on the right-hand side. Let me move the slides too, so we remember what we were doing. So on the right side, the way I'm going to implement this, I'm going to implement it in 2 steps. I'm going to type in the ghost value and then plug in the ghost value over here. Makes sense? So let's keep this here. Still have people joining. Okay. So I'm going to the right hand side and I'm going to keep these here for a second because I'm going to overwrite them. So everything is set up here correctly, right? This is k over delta x k times phi I plus 1 minus 2 phi I plus phi I minus 1 over delta x squared, or phi I minus 1 minus 2 phi I plus phi I plus 1 over delta x squared. So this still holds. I'm going to keep this and I will just overwrite now the Newman condition on the right boundary. Okay, so on the right boundary, I have the ghost value, or phi ghost, let me say, let's say beta is equal, so we put Newman equals 0. We start with Newman equals 0. And then we say phi ghost, that's the ghost point, that's 2 times, so 2 times beta times dx plus phi n minus 1. Okay, phi n minus 1. So what is phi n minus 1? In this case, it's, so remember, phi, we have access to the entire array of values here, right, through phi. So phi n minus 1, phi n is the last point, phi n minus 1 is the second from last, correct? So what I can do is access phi minus 2. Agreed? So if I were to put phi minus 1 here, it would access phi n. So that's wrong. I need phi n minus 1. I need this point over here. Okay? So that's why I put phi minus 2. And then finally, now I correct the right-hand side. Remember, my right-hand side is this guy now at point n. So right-hand side at the last point, at point n, is going to be equal to, so I'm going to correct this. I'm going to copy, well, I don't need to copy this, sorry. So I'm going to do, this is k over delta x times, excuse me, times the last one is going to be phi, it's going to be phi minus 2. Okay, so what I'm doing, I'm implementing this formula. Phi n minus 1, it's phi minus 2, that's this point, minus 2 phi n, that's the last point here, plus the ghost point. So see how I'm going to implement this. Phi minus 2 minus 2 times phi n, and then plus phi ghost. Okay, so you could have implemented it in this way directly, like 2 beta delta x over delta x squared. I chose to do it in 2 steps. Okay, does that make sense? Does this make sense? Okay, sorry, I can't see you guys. Okay, now I can see you. Does this make sense? Okay, perfect. So, sorry, my face is looking on my other screen as I'm typing. So, yeah. So for Mason, Olivier, can you turn on your camera so I can see you, please? Okay. So now, what does d phi by dx do? What does the Newman condition tell us? So this is the slope. This is the slope at that boundary. So if the slope is 0, it means it has to stay flat. Now this is, remember, this is a telltale sign about Newman conditions that we tested back when we did the linear system of equations to check the boundary conditions. If the Newman condition is 0, the curve needs to be perpendicular to the boundary. Okay, so that's a very important test to check for the correctness of an implementation. Now, if d phi by dx is positive on the right boundary, then the curve needs to be going up on the right boundary, right? Because then you're saying phi outside the boundary minus phi inside the boundary over delta x is positive. So phi outside the boundary must be greater than phi inside the boundary, correct? And therefore, the curve needs to be sloping up. Okay? When the Newman condition is negative, then it's going down because this is saying phi outside the boundary minus phi inside the boundary over the distance is negative, that means phi outside the bound that means phi inside the boundary is larger than phi outside the boundary. Now the opposite is going to be true on the left boundary, right? Because you're always the approximation for the derivative is going in the positive x-axis. Okay, so we'll see that. So let's start first with the zero Newman condition here. So what we should expect, I'm gonna drive this to maybe 64 points just for it to be faster. Okay, so what we should expect here is that the right boundary is still flat, which is correct. That's a good sign that we're doing this correctly. I can plot at a few other points as well. Let's stay, so after 10 time steps, it's starting to diffuse, and then it's staying flat at the boundary. So that's good. Now let's go and experiment. Let's put beta equal 1. Now the slope should be going up on the right boundary. Agreed? Because we are pushing that value upwards. Okay? And then if we run it, look at that. It's correct. The value is going to change throughout the calculation because what it depends on the interior value. But it might continue rising until it reaches a steady state. But notice at least the slope, notice at those two red curves, they are parallel to each other at the boundary because that slope is exactly equal to beta. Okay? Is exactly equal to beta. And as expected, when beta is positive, the slope is going up on the right boundary. Okay, so let's do a negative beta now. If we do -1, it should be decreasing, and look at that. It is indeed decreasing, and it will continue decreasing like that until it reaches a steady value that's determined by the system and the initial conditions. Okay, that's the uncertainty with a flux. When you specify a flux boundary condition, the solution is up to an additive constant. The value that it reaches is going to be determined by the initial condition and the system dynamics overall. So you're not specifying a fixed value, you're specifying the rate. And so that rate can float as the system evolves. So don't be surprised as you see that value go down over time, okay? Or go up over time. Now let's do the left boundary. So I'm gonna copy this and paste it. Newman condition on the left boundary. And I'm gonna call this alpha on the left boundary. Now, when we do this on the left boundary, then my phi 0 is my ghost point. Okay, so phi 0 is my ghost point as shown here in the slide. Okay, so now phi 0 is going to be minus 2 alpha delta x plus phi 2. Okay, so if you invert this equation, minus 2 alpha delta x plus phi 2, right? So what I will do here is minus 2 alpha delta x plus phi 2, simply going to be actually phi at 1, because that's the first interior point. Phi 0 is the boundary point. Phi at 0 in Python is the boundary point. Phi at 1 is the second interior point, which corresponds to phi 2 over here in our human understanding of the nomenclature. Okay, so my indices here are based on 1. The indices at Python are based in 0. So this would be it. Now we have to fix this a little bit on the left boundary. Okay, so I have on the left boundary, I'm going to do phi I plus 1. Okay, so that's phi 1 minus 2 phi 0 plus phi minus 1, right? So this will be phi 1 minus 2 phi 0 plus phi ghost, okay, times k over delta x squared. Is this clear for this one? If it's not clear, let me know. We can dig through it. So those who don't have a thumbs up, is it the thumbs down? Okay, so remember what I'm doing here, I'm doing this in a two-step process. I'm computing phi ghost and I'm storing it temporarily in a value here. Okay, and then I'm saying, well, the equation over here is phi 2 minus 2 phi 1 plus phi 0, which is the ghost point. So that's first interior point minus 2 times phi at the boundary plus phi ghost. This is it. Phi interior point minus 2 times phi at the boundary plus phi ghost. Okay? Thomas?
Why is the RHS for the left-hand side 0?
Yes.
-1 and not 0.
It should be 0. Correct. Good catch. Yep. Good catch. Okay, so those here are for Dirichlet conditions, but I'm overwriting them down here. So, you know, I can comment them or just remove them. It doesn't matter. Okay. So let's run this. Now, alpha on the left-hand side, I'm saying d phi by dx is negative. Okay, d phi by dx is negative. So what is the slope going to look like? It's going to be coming down. No, yeah. So whatever, it's our hands are inverted on the camera, right? So the value inside is going to be the value. So d phi by dx, we're saying it's negative. It's going to be value on the inside minus value on the outside over delta x. So this means the value on the outside is greater than the value on the inside. So slope is going to be coming down. It's the opposite of what happens on the other side. Okay? So let's see this. Indeed, alpha negative on the left boundary, the slope is going to be coming down, right? Because that means the value outside the boundary is greater than the value inside the boundary. So if you think about it, it's like you're feeding heat into the system on the left-hand side, but you're withdrawing heat on the right-hand side. Okay? In other words, like there is a fictitious value outside the left boundary that's higher, so it means it's bringing in information, bringing in heat, but then on the right-hand side is drawing all of that heat away. Okay? And the opposite is true on the left boundary. So if alpha is positive, that means that the interior value is greater, indeed. So the interior, yep, exactly. So the slope is going up on the left, but on the right, it's coming down. This is very important once you go in 2 dimensions and you implement Newman conditions in 2 dimensions. When the Newman condition is 0, all your contour lines need to be perpendicular to the boundaries. Okay, that's how you check you implemented your Newman condition correctly. It's very hard to debug things in 2 or 3 dimensions, but one way to check, you look at your contour lines, and if they're perpendicular to the boundary, you have Newman 0. If your Newman is positive or negative, then slope is up or slope is down. Okay, so that's how you reason with visualization to make sure you got your boundary conditions correct. Okay? I see some eyes squinting. No? Okay, all good? Sorry, I'm not in person, so I cannot gauge your body language. So I appreciate if you give me feedback. Okay, so let's continue. So now Newman condition is behind us. Okay, the next topic I want to talk about is a variable diffusion coefficient. So one of your colleagues asked about that last time. We'll talk about it today. It's just to add some nonlinearity to the problem. So a variable diffusion coefficient would alter the diffusion equation or the diffusion term. If you remember, our form was div k grad phi, correct? That was the diffusion term. It was divergence of the diffusive flux, which was minus k grad phi, and then the minus sign outside. So if k is not constant, you have to keep it inside the divergence. Okay, it will remain div k grad t. Okay, so or div k grad phi. Sorry. So in 1D, it would look like this: d by dx of k, d phi by dx. Now k could be a function of x, could be a function of phi, or both. Whatever, it doesn't matter. Normally, it's given to you as a formula that you can plug in. But our interest here is how do we convert this into discretization so we can build the system again of ODEs? Well, one approach is to do two approximations. The first one, on the outside derivative, we do a backward difference approximation. On the inside derivative, we do a forward difference approximation. Why is that choice? Is because when k is constant, it's this approximation that gives you the central scheme that we've been using. That gives you phi I plus 1 minus 2 phi I plus phi I minus 1. It's a combined forward and backward difference. So you might say, okay, let's apply the same approach. Let's do a backward and forward difference. So if we start with the backward difference, so that's the outside derivative, it should be k d phi by dx at I minus k d phi by dx at I minus 1. Okay? So now what is k d phi by dx at I? It means this is k at I times d phi by dx at I. And k d phi by dx at I minus 1, it means it's k I minus 1 d phi by dx at I minus 1. Okay? Can you see my cursor? Perfect. Yeah. Okay. So then you do a forward difference on the remaining derivatives. Then d phi by dx becomes phi I plus 1 minus phi I over delta x, and then you get the delta x squared and so on, right? And then on the second one, you also do a forward difference, phi I minus phi I minus 1 over delta x, and then that gives you delta x squared. Okay, and the resulting scheme looks like this. But there's a problem with this, because you see diffusion, we said that diffusion is trying to average things by communicating information through the neighbors. If you have phi I, you have phi I plus 1 and phi I minus 1, right? But there's a problem in this formula in that, okay, for the phis, I can see phi I plus 1, I can see phi I, and I can see phi I minus 1. But for the k, I'm only seeing ki and ki minus 1. I want to see ki plus 1. So this is biasing the solution towards the left-hand side of the information. So if k is a function that's changing in space, we're only using information from k towards the left, not averaging, I want ki plus 1 to be involved somehow. So then a better formula for this would be to say, okay, instead of taking ki, I'm going to take the average between ki and ki plus 1. And instead of ki minus 1, I'm going to take the average of ki minus 1 and ki. Now, this comes from what we call finite volume approximations. So don't worry about that. Just know that this is one of the best formulas you could use to discretize this. Would this first formula I showed work? Absolutely, it will work, it will be okay. But the lower one is going to be more accurate, okay, because it's balancing everything around that point I that you're discretizing, okay? So this is just a little bit more complicated than the standard stencil, the standard second derivative approximation we were doing, okay? But we can do it with numpy.roll, no question, no issues. So here are the formulas, ki and ki plus 1 over 2. You just do numpy.roll on k, and then numpy.roll on this one, numpy.roll on ki minus 1, and then on phi I and phi I minus 1. Okay, so this is following the standard approach that we have been using all along. Okay, you might need to do a boundary condition on k. I'm not gonna worry about that because I'm assuming Dirichlet conditions here or Newman conditions. Dirichlet conditions, you don't need to worry about the boundary conditions on k because you're immediately specifying the value of phi. Okay, Newman conditions, you might need to take this into consideration, which would be a nice homework problem. All right, so what are we going to do next? We will solve this same problem. We're going to diffuse the Heaviside function, but I'm going to give it a Heaviside function in the diffusivity, and it's going to be discontinuous. So in the lower half of the domain, from 0 to 1.5, my value of k is going to be about 0.1. And then on the second half of the domain, my diffusion coefficient is going to be 1.1. Okay? So there's a step change in diffusion. What we should expect from this is the Heaviside pulse that we're diffusing is going to diffuse faster on the right-hand side of the domain and slower on the left-hand side of the domain. Agreed? Okay. So let's go ahead and implement this. I'm going to create I'm going to duplicate my this file. Okay, so I'm going to duplicate and okay, so this is a duplicate in class diffusion coefficient, diffusion equation with variable coefficient. Okay, perfect. So everything will remain the same, except now I need to create a heaviside function for the diffusion coefficient. Okay, so I'm going to define diffusion coefficient as a function of x, and I'm going to return np dot, so let me see what I put here, heaviside x minus a, and a, let's say 1.5. So heaviside of x minus 1.5. Now the value, so if you look at, I cannot see the documentation here. Let me run this first. Okay, so now the documentation is saying this is heaviside function x1 and x2. x1 is the point where below x1 the value should be 0, and above x1 the value should be 1. Well, technically what they allow you to do, the value below x1 is going to be x2, and above x1 it will be hold on. So heaviside x1, x2. If it's less than x1, if x1 is less than 0, then it's 0. If it's equal to x2, it's equal to x2 if x1 is 0, and then equal to 1 if x1 is greater than 0. Okay, so this is great. So what I will do here, I will put 0.1 over here plus 0.1. So when it's less than 1.5, this is 0. So I'm going to add 0.1 to it. Okay, because I cannot have a 0 diffusion coefficient, it will not move. So I'll add 0.1. Then when it's above 1.5, this function will return 1, and then we're adding 0.1 to it, so it becomes 1.1, just like I'm showing here. Okay, now I'm going to comment out the Newman conditions. I don't want to worry about that, and I'm going to uncomment this, but let's go ahead now and implement this with the diffusion, with the variable diffusion coefficient. Okay, so let me see. Right hand side is set to 0. So what I need to do now, k over here is the name of this function. Okay, is the name of this function. So my k is k of x, right? So x is a global variable that's being passed along, so we're good there. And this k, it could be an array if you want. You can send it in as an array, but I'm sending it as a function name right now, okay? So that I can compute it inside in here internally. Okay, so let's go ahead and implement these. I'm gonna call this k plus. So k plus is equal to k plus numpy dot roll of, k underscore plus numpy dot roll. So k underscore is an array of k values, okay, is the array of k values at all the x values, okay? Now, like I said, you could pass k as an array over here, it's up to you. Instead, I passed the function name, and I'm calling it in here, okay? Either way would work, okay? If you had passed k as an array, you don't need this line anymore. Okay, so numpy dot roll, k underscore, and I'm going to shift by -1, shift equal -1. So that's ki plus 1, and then over 2. Okay, so that's the k plus, and then the phi plus, that's phi I plus 1 minus phi I over delta x squared, and that will be numpy dot roll and phi shift equal -1, that's phi I plus 1, minus phi I, that's phi, over dx squared. Then k minus is equal to, so I call them k plus because it's I plus 1, k minus, it's I minus, has the I minus 1 in it. And this will be k plus numpy dot roll, k, and then shift equal 1, and that's over 2. And then phi minus is equal to, so that's phi I minus 1 over delta x squared. So this would be phi I minus numpy dot roll, phi, and then shift equal 1, and that's over delta x squared. And finally, my right hand side, everywhere except the Dirichlet boundaries, my right hand side is going to be this formula up here: k plus times phi plus minus k minus times phi minus. Okay, so see, everything has to do with the right hand side of these equations. Once you figure that out, you're good to go. So this would be k plus times phi plus minus k minus times phi minus. Okay, and then on the boundary conditions, I have Dirichlet conditions, and those are fixed from the initial condition. So my right hand sides are 0 here. I don't need to worry about this. Return right hand side. I'm gonna execute this, and then okay, so we should be ready to go. Yep, except here my arguments, my k function, I need to pass on the name of the function, and that will be diffusion coef. Okay, so Python is very smart. Whether you pass a value or the name of a function, it will figure that out. Okay, all you have to do is pass the name of the function. This is just exactly like we did when we were using root and all of the other functionality, right? So if you run this, and let's run it, haha, look at that. So notice what's happening. After some time, after what, 10 time steps, it's diffusing faster on the right side of the domain. But look at 1.5, this is where there's this step change in k. See how the diffusion is changing as you move from the region of 1.5 to the region of above 1.5. Did you guys get this result? Yes? No? Okay, who wants me to, you want me to go back to the code up here? Okay. Feel free to just speak up. I can't see what's on your laptops, what's on your computer, what's on your code. So now play around or create an animation with this. It will be really cool. And oftentimes you have step change like that when you have multi-materials laid over each other, right? Like in the walls in your home, you have drywall, and then you have insulation, and then you might have a gap, an air gap. So your K will be discontinuous like that. Okay, so you will see this step change like this. One time I had a little side project. We were looking at heat transfer inside the tooth. They were trying to apply a cryogenic cooler at the crown of the tooth and see how fast it will cool all the way to the root. Now you have your dentine, and then you have your the pulp on the inside, and then you have the outside, right? So you have multiple K values that vary significantly from one material to another. So you do have this sort of step change. Okay, you can smooth it out with a sigmoid function, but if it's stable and running, this is as good as it gets. Okay, everybody got the same result here? Did anyone not get this result yet? I have no idea. Who else is still working on this? Okay, so yeah, where are you stuck, guys?
I just am typing things wrong, so I'm just like debugging it a little.
Pardon
so
me?
like it's not. I'm just typing things wrong. So
Okay.
Yeah, so I'm just it's.
Just gotcha. Okay. Do you still want to look at the code here?
No, I think I'm good.
Okay, Thomas.
I think I'm good.
Okay, you got this. Still giving you an error. I can't hear you.
Oh, it's all good. It's upset at the line.
Which line?
Where it's the k underscore is equal to k of x.
Okay.
It's saying that it's not like a float object is not subscriptable.
Did you pass the name of the diffusion coefficient function?
So I see. I think that's what it is.
You were passing the value k, so it's trying to apply a number as a function of x, which doesn't make sense. So that's the unsubscribable. So usually it's just you're missing out a function name. That should fix it.
Perfect. Thank you.
You got it?
Yeah.
Okay. We good to move on? All right. Excellent. So next we will tackle systems of equations, right? See how we're ramping up the complexity. You guys are gonna come out of this. I hope you remember everything we've done here, or at least come back to these lectures. These are super powerful tools that you will have with you for your research, for your career. You might forget some of them, come back to these lectures, but I'm going to try to cover all possible combinations of things within reason that we can do with this. The next complexity we will add is a system of equations. We're still in one-dimensional space, but we're going to do a system of equations right now. So the example I will give, and some of the most interesting cases you will see are actually diffusion reaction equations. Convection, not yet, but there's no flow field available. These are diffusion reaction equations. And if you go back all the way to the mid-century, if you know of Alan Turing, he was one of the first people to develop this system. It's called the Turing diffusion reaction system, as an attempt to model complexity in cells in the human body. So he was the first mathematician. He was a genius, and he developed the computer essentially. And so the theory of the computer. And he was the first to develop this diffusion reaction system that creates complexity from simplicity. And it's just only a diffusion reaction system. All right, so we're going to do an example like that. And the reaction we will take is a simple reaction. You have two reactants, A and B, and together they're producing C, being created by this reaction. The reaction rate is some constant times concentration of A, concentration of B, and Ca, Cb, and Cc are the concentrations. That's what we are interested in. So we have some initial concentration of A and B with some boundary conditions, like you have a feed system or something, and we're going to see how the system diffuses in your reactor and how it reacts. So reaction is going to consume A and B, and it's going to produce C. Great. So there's going to be plus and minus in the source term. Now, using our general conservation law with a Fickian diffusion model for these reactions, it would look like this in general 3 dimensions. The rate of change of the concentration for any of the species A, B, and C is div d grad C. So now, because this is a reaction system, I don't call it K anymore. K is more for heat transfer diffusivity. D is when you're talking about reactions and mass transfer. That's the mass diffusivity of reactants of species, of things that are changing concentration, plus some source term. I don't have advection over here. Okay. Now, I define, again, like I said, Ci corresponds to the concentration of species I. Di is the diffusion coefficient of species I, because each species is gonna have a mass diffusivity that's different. So in the heat transfer problem, we had materials stacked next to each other and they had different diffusivities, like the problem we just did. Over here, all the materials are mixed, okay, but they have different, each material has a different diffusivity than the other, okay? And SI is the source term, so I have a little typo here. SI is the source term corresponding to species I, okay? Now, in one dimensions, this becomes just straight out first derivatives, and we have three equations for this. The for concentration of species A, you have the rate of change in time equal this diffusion term, and I'm assuming the diffusivity of A is a function of space and the concentration of A. Okay, so I'm gonna keep it in the derivative. And then because I'm depleting A, and the rate of depletion is the reaction constant K times concentration of A times concentration of B. This is like a first order reaction. So A and B combine. KCACB is how much we're taking out of A. And same thing for CB. We're taking out K times CA times CB. And you have this diffusion term. Everything is a function of B. And finally for C, notice the sign change for the source term. We're depleting A and B, so we take out of them. And then we're adding into C, so we add plus K CACB. Okay, so it's fully conservative system. And then if you further assume that the diffusion coefficients are constant, then you have this simplification, which is exactly the type of problem we were working with. We know how to do this already with the Dirichlet conditions. And normally for these cases, you're working with Dirichlet conditions. We can work with Newman, then the system is just mixing, isolated from everything else. Again, that can be applicable like we did earlier. We're gonna solve it with Dirichlet conditions next. Except now, you have a source term, which is not very hard to implement. You don't need any numpy.roll or anything here because the source term is just these fixed values. There's no derivatives involved. But the complexity that we added here is instead of having one PDE, we have three PDEs now. So if we want to solve this on this domain with these Dirichlet conditions, 5 for concentration of A on the left, and then 0 and 0 for B and C on the left, and then on the right 0 for A, and there's some value for B, and C is 0. So we know how to do this numerically, and with some initial conditions, we can put a Gaussian on A, and then a constant on B, and then 0 on C, or we can play around with that. In the end, it's not going to matter because the Dirichlet conditions are going to dictate the final state of the system. But the complexity here is really coming not from the physics, it's coming from how we're going to implement this in Python. Okay, so when we did one PDE with n grid points, we had n ODEs. Agreed? One PDE at n grid points, we had n ODEs because we had one ODE per grid point. Now you have three PDEs, so you're going to have three ODEs per grid points. So your system is going to be a total of 3 n ODEs. Okay? Now the question is, how do you organize these ODEs in Solve IVP? Do you put at each grid point ODE of A, ODE of B, ODE of C, and then on the next grid point ODE A, ODE B, ODE C, and so on? Or do you put all the ODEs for A, and then after them all the ODEs for B, and then after them all the ODEs for C? It doesn't matter. ODE in Solve IVP will figure it out. But from our perspective, as we are doing all the slicing and the rolling, it makes more sense to put the first PDE first. So the first n equations will correspond to A, the second n equations will correspond to B, and the third n equations will correspond to C. Okay, that's a cleaner way of doing it because it will simplify the programming of things. All right, now our solution array will then consist of 3 n equations. We are going to treat this as if we're doing one PDE at a time. So we have n equations for the first PDE, n for the second PDE, and n for the third PDE. Then what we will do we're gonna concatenate them. So there's a new tool that we're gonna learn today. From NumPy, we're gonna concatenate, which means we're gonna put all of these equations back to back. Because solve IVP, it just needs one list of equations. It doesn't care if you're doing PDEA, PDEB, PDEC. It just deals with a system of ODEs, right? So we're gonna concatenate, put all of these ODEs into one big array of size 3 times n, and then ship that off to Python. Okay, so let's see how we do this. I'm gonna duplicate the other one, not the variable diffusivity. I'm going to duplicate this guy. Okay, I'm gonna duplicate this guy because I have the diffusion formula set up in there. Okay, and okay, so let's duplicate unsteady diffusion class. Okay, duplicate. We're gonna do this. Okay, so duplicate whichever notebook you want to begin with. I'm gonna duplicate the one where we had only diffusion. So this is essentially exercise number 4 in class diffusion reaction system of equations. So if you are taking advanced numerical methods with Professor Sutherland, you probably worked on this assignment using your own nonlinear solver. Does this ring a bell? Yeah? Yeah. Okay, perfect. So it's going to be much easier doing it here with this approach. Okay. All right. So what I'm going to keep the Heaviside source, or the Gaussian source actually, because I will need that, and I'm going to put it in the middle, maybe here. Again, it doesn't matter. Now, what I need to do is set up a few things. Hold on. Let me see what I did here. All right, so I'm going to set up a few things. Before I set up the right-hand side, I need to set up a few things first. Here, I'm going to put L is equal 1.0, and then diffusion coefficient for A is going to be 20 e to the minus 4. So 20.0 e to the minus 4 is going to be meters squared per second. And then diffusivity for B is 10 e to the minus 4, and diffusivity of C is going to be 5 e to the minus 4. For the boundary conditions, concentration of A on the left is equal to 5, so that would be moles per cubic meter, again stuff per unit volume. And then concentration of A on the right is going to be 0.0. Concentration of B, CB on the left. So that's the problem I'm setting up here, okay, this problem. Okay, concentration of B on the left is 0.0. Concentration of B on the right is 3.0, and then concentration of C on the left is 0.0, and concentration of C on the right is 0.0. Again, so C is a product. It's not, I'm going to put it 0 everywhere. I'm not feeding C. It doesn't do anything, doesn't react. What I care about is feeding A and B. So we're feeding A from the left and feeding B from the right, and we're going to have an initial condition on A and B. Okay? Now, for the diffusion system, what I'm going to assume is that, okay, so I have I'm gonna have my phi value here. Let's call it C for concentration. Okay, let's call it C. So now C is an array, is a 1D array of size 3n, where n is the number of grid points. Okay, so we have three PDEs. Okay, the first n entries in C, we choose that they correspond to CA, the second n entries to CB, the last n entries to CC. Okay, so the first thing I want to do is logically I'm thinking A, B, and C. Solve IVP doesn't care, it's just a system of equations. So I want to segregate, I want to access CA, CB, and CC separately. Okay, so what I can do is say CA is equal to all the concentrations of C, the first n concentrations. So what I did here, I accessed the first n values in the total array of C, and then CB is going to be the next n value, so it's going to go from n to 2 times n, and then finally the last n values, CC will be C from 2 times n all the way to the end. Okay, give this a second to think about it. C is a full array, has 3 n values. The first n correspond to concentration of A, the second n set corresponds to B, and the third n corresponds to C. What I'm doing here, I'm separating those for a minute because logically from the human mind, I want to segregate A, B, and C, work on each, and then combine them back together. Okay, so now it's as if I have a solve IVP for CA, solve IVP for CB, and solve IVP for CC, and I can build those equations like we would normally do. Okay, so let's do it. For right-hand side of A, I have dA times, and then the standard diffusion coefficient here. So the standard diffusion formula, so which we already have here. So I'm going to modify this a little bit. Right now I have dA instead of K over delta X squared, and then instead of phi I have CA, and CA. Does it make sense? So this is saying the right-hand side for the A equation is CA at I minus 1 minus 2CA at I plus CA at I plus 1. Okay? And then right-hand side of A at 0 is 0, so that's Dirichlet, and then right-hand side of A at the last point is 0.0. Now, next we do B and then C, right? So B, now for B, it's RHS of B, RHS of B, and then this is DB, and then CB, CB, and CB, and finally for C, CC, and then CC. Now, what does CB, CA, CC contain? They contain the values that the solve IVP is working on. We're just kind of updating them as it's trying to do the time advance. Okay, so once we do this, we're done. Okay, there's no Newman, there's none of this stuff here. I'm gonna erase all of this. Okay, and that's it. Okay, now before we return, okay, I need to concatenate all of these things. Okay, so RHS is gonna be, I can delete this one here if I want. RHS will be numpy dot concatenate, and you need 2 parentheses here, RHS-A, RHS-B, RHS-C. So now we went back to what solve IVP understands, a huge list of ODEs, and then it's just gonna solve them, does its thing. But then logically, once we go back to the right-hand side from the human mind, we need to separate CA, CB, and CC, okay? You want a minute here? Catch up? Who's still working on it? Okay. If you just copy paste, because we've done it, once you do it once, just reuse. Ideally, we would create a subroutine that we would call and call over and over again, right? So we don't have to worry about this. Okay, can I move on? All right, so let me execute this. I'm gonna execute this, okay? And then I have this information here. Now I need to define my domain. So I already have L defined up here, L equal to 1, then X linspace, dx. I don't have K anymore. And my initial condition, now I'm going to have 3 initial conditions, right? I'm going to have 3 initial conditions. So for for IC, the initial condition for A is going to be my Gaussian. So Gaussian is going to be Gaussian initial condition, right? That's what we decided, Gaussian initial condition. And remember, because this is Dirichlet, I need to set the initial condition correctly. So on the left-hand side, I have CA left, and on the right-hand side, I have CA right. Agreed? Now, let's do B and C. I'm gonna copy this twice. For B, I'm gonna call this B. For B, I said I wanted a fixed value for B, just like 1. Okay, so np.ones of size n. Okay, there's n grid points. And then ICB at 0 is CBL, the value of CB at the left boundary, and ICB at the right boundary is CB at the right boundary. And finally, the initial condition for C, let's call it capital C, is zeros, mp.zeros of size n, and then this would be CCL and CC right. Okay. Now I have three initial conditions. I also need to concatenate them because solve IVP takes one system of initial conditions. So my total initial condition will be, so IC total is equal numpy dot concatenate, and then ICA, ICB, and then ICC, right? And that's it. So let's comment this out. Let's see if we can do this from 0. Let me see what I did it here. T final, maybe put 100. Okay, and then we'll evaluate it at a fixed time, and then solve IVP. Let's rename this to diffusion reaction right hand side. Diffusion reaction right hand side. I'm going to execute here, and this will be diffusion reaction right hand side. The span is from T0 to TF. Now the initial condition is IC total. The arguments are going to be, so I don't have I don't need a diffusion coefficient here. You could pass it, but I'm not gonna, because I declared it globally here. So I'm gonna skip this and just put dx, and we will use a BDF method because this is pure diffusion. It's likely to be stiff. And so, wow, we solved it, no errors. Okay, so now we need to plot the solution. Now, what does solution.y contain? It contains all of the equations 3 times n at all the times. So we have 100 times steps from t eval and 3 times n. So 3 times 64. So let's see, sol.y.shape. It's 192 by 100. So 192 is 3 times 64, right? So the first n solutions will correspond to CA. The second n solutions will correspond to CB. And the third n solutions will correspond to CC. So now we're gonna do the opposite of concatenate so that we can access CA, CB, and CT in time. So here's how we will do this. CA is sol.y. I'm going to take the first n values, okay, the first n values in the solution, but all the times. So in the first index, I have the values of the solution. In the second index, I have the times, right? If you look at the shape of the solution, it was 192 by 100. So the first index contains the solutions, the second index contains the times. Now I want to take CA only at all times. So I will keep a semicolon on the second index and semicolon to n on the first index. So that will give me CA. And then now if you look at CA.shape, it will be 64 by 100. So 100 time steps at each of the 64 grid points, okay? Same thing for CB. CB is sol.y, but this time I'm going from n to 2 times n at all times. And finally, CC is sol.y from 2 times n to the end, okay? Okay. So for sure, I will ask you about slicing in the final exam. 100%, guaranteed. Okay, so make sure you know these symbols. Okay, so now I have CA, CB, CC at all times. Okay, moving on, I just need to plot those. I'm gonna delete this and I'm gonna create a new cell, and then okay, plt.plot. So let's define time index is 0, so that's the initial condition. plt.plot x and then CA. Okay, at now I want to plot CA at all grid points, but only at time index. Okay, so now we're inverting things again, and this is label equals CA. Okay, and then I'll copy paste, and then we will do CB and CC. CB and CC. Okay, so the initial, oof, good, it worked. Okay, so plt.grid. All right, so now we have the initial condition as expected. We have the Gaussian, let's put the label, plt.legend. So the blue one is CA, the orange one is CB, and the green one is CC. Now notice CC is 0 everywhere. CA is a Gaussian, but because of my Dirichlet condition, it goes to 5 on the left boundary and goes to 0 on the right boundary. Okay, so there's this kind of step change at the boundaries. That's okay. And then finally for CB, the orange one, it's 1, but goes to 0 on the left boundary because I'm not feeding anything on the left boundary, and I'm feeding a value on the right boundary. Okay, now remember there's no points between the last 2 points. That straight line shouldn't exist there. It's just 1 point and then suddenly it steps up to the top. Okay, so let's take the first time step. Okay, it's changing. Then like after 10 time steps, okay, it's changing. Oh, well, nothing is happening. What happened? We forgot. What did we forget? Nothing is happening on C. Did we forget something? Only A and B are diffusing, but C is not being created. Why?
We didn't include the source terms.
Correct. Thank you, Eric. I appreciate it. Okay, so now we forgot the source terms. So what we would need to do is put in the source terms. And so here for A, we have minus, and what did we have for KA? We had KA, we didn't actually put the K's yet in the code. So I need to declare, well, there's one reaction constant. So I'm gonna put it as K is equal to 100, let's say, okay? We'll play around with that number. So minus K times CA times CB. And then here, minus K times CA times CB. and then over here plus K times CACB. So execute, execute. Chip. Aha. So now we're seeing a difference. So let's go back to 0. It's 0, and then we go one time step. Whoa, suddenly you see this huge jump in C, in green, and then it kind of climbs up, right? Hold on, do I have this right? CA, CB, CC. Because like C diffused really quickly. Hold on. And then 2, then time index -1. This is what's happening, okay? So at 10, so notice CA sort of diffused really quickly. Okay, the initial condition didn't matter. I told you in the end, the initial condition is not going to matter. It's what the boundary conditions are going to determine. And then you see CA is being tugged on the left because we're feeding CA on the left. CB is being tugged on the right. We're feeding CB on the right. And CC is being created based on that initial condition where we had CA and CB. So that's going to remain in the system, right? But then it will continue changing. And then you go to 20 time steps, or the last time step at -1, it's going to start stabilizing at this condition. Now, this will eventually reach steady state, but it will take a very long time. So you have to go to T final maybe 1000. So I'll put 1000 over here. And then you see it just continues climbing all the way. Okay? Now, you could solve this at steady state. We know how to do it. It's a system of nonlinear equations. At steady state, you take out the time derivative, you do the discretization, but the source term is nonlinear because it's multiplying two concentrations. And then you can do root, to do the steady state, and you can compare with this solution at long time, because at long times, that time derivative, hopefully, for the system is going to go to 0. So it will converge to a steady state, and that should be exactly the same answer as the steady state system if we were to solve the steady state system. And that's why the initial conditions didn't matter. Because for the steady state system, there's no initial conditions, it's only boundary conditions. Okay? So that's a peculiar case about these Dirichlet conditions. When you have a diffusion system with Dirichlet conditions, the initial conditions are not going to matter. Okay, think about the steady state condition. Okay, so this is really cool. Okay, now you can do a system of, this is a system of nonlinear PDEs. Okay, and it just does the job, it just does work. Okay, the only thing we had to do was the concatenate. Okay, to stack them and to separate them and then stack them. And then once we get the solution, we separate them again. That's the only logic we need to do. Okay. You're either blown away by how awesome this is, or like you now I have no idea what happened. But I hope one day you will really, really appreciate what we're doing here. Ask those taking advanced numerical methods how many thousands of lines you had to code up to do this with an implicit method, with an implicit time integrator, and you had to build the Jacobian and the derivatives and all of that nastiness. So this is done in a few lines of code, dozen lines of code. So really you should appreciate that there's a lot that is going on behind the scenes here that's making this work. There's a lot going on behind the scenes. Okay? One day I hope you'll appreciate this. If not, I hope you can use it to solve your homework problems or any research problems. Okay, so if you're modeling a system in your research and you end up with a diffusion advection system of equations, well, you can come back to this lecture and do it this way. This is a robust approach, okay? Thanks to this Solve IVP. What is going on inside Solve IVP is nothing short of a miracle, frankly. Let me put it this way, if we didn't have Solve IVP, I would not be teaching you how to solve partial differential equations numerically. I wouldn't. We would only be stuck at linear systems and the nonlinear system of equations, we wouldn't even dare to touch unsteady partial differential equations. Out of the question. So thanks to Solve IVP, this is all possible. Okay, and literally the sky is the limit. You'll see what we're gonna do with when we go to 2 dimensions. Okay, it's really, really cool stuff. So I hope you appreciate this, but learn it, put some effort into it, see the logic, the unique logic. I don't know of anyone frankly doing this anywhere. I scan, I look on YouTube, I look on the internet, anyone using Solve IVP in this approach, in this method. So benefit from it, okay? Because the alternative is very, very complicated. Or no solving PDEs, okay? Godspeed and see you on Thursday. Bye-bye.